Gym-Scarecrow, Sentinel Conservation via Aerial Reconnaissance and Escort.
Hello everyone and welcome back to my channel. In today's video we're going to have a short description of how Adam's system works, along with a short demo of the system working. So without further ado, I'll pass it off to Adam and he can show you how his system works.
Thanks, Ian. So as Ian mentioned, I'm working on the autonomy portion of the project. So what that means is I'm working on the algorithms and the processes which take the observations from the agent through the base station into my framework, make a decision, and then pass that decision back out through the base station to the agent so that it can move and chase down the pigs and drive them out of the keep out zone. Now, the way I went about doing this is I created this gym-scarecrow module. So this is a Python module. And this Python module creates a gym-scarecrow gym environment. So if you're not familiar, the gym environment is an OpenAI gym environment. OpenAI gym is a framework which is developed for reinforcement learning that sets up kind of a standard way of passing in observations, passing out actions, and evaluating performance. So that way it can grow and create better algorithms, better policies to be able to control the agent and complete the mission. So for us, our mission is driving pigs away from a keep out zone. And so I'm getting in observations of where the pigs are, where the UAV is, and then I'm passing out actions. And we'll get into that more here in a little bit. So there's three main pieces to my my framework here that I've developed. And so one is the controllers. So this is where all the different controllers live. So as Ian mentioned, we have a human controller, various AI controllers, and a rule-based controller. And I'll dive deeper into those here in a little bit. The environment. So the environment is a simulated environment that I created, but it also has the ability to ingest live data from the hardware system and then show the live data in the simulated environment. So you can see on your machine what's happening in the real world. And then also pass out the intelligent actions from the algorithms and controllers. Main just takes on all the parameters and executes based on the parameters what type of simulation you want to run. So if we open the parameters here, in the parameters, there's some visual parameters, which is just how you want to set up the environment, keep out zone size, things like that. And then we get down to the autonomy parameters. So in the autonomy parameters, you can set the algorithm that you want to use. So human, it would be the algorithm, and you can control the UAV. Q-learning is a tabular reinforcement learning algorithm that I'm using. And then we have the rule-based system, which I developed, which I'll get into a little bit here of how that works and why I designed it the way I did. And then coming soon, I think that we should look into, and I've already started looking into, a deep Q network and a proximal policy optimization algorithm. And my reason for this is our state space is pretty large, and I had to quantize it down a lot to be able to use a Q-learning approach, a tabular approach. I think it'd be much better to use a function approximating approach where you can take much more information-rich input features and observations to learn an effective action policy. Hardware, so this is a toggle to turn hardware on or off. So if hardware is false, then it just uses the simulation environment that I developed, the fully virtual simulation environment. If it's toggled to true, it gets all the observations and input data from the live system, hardware system, and passes out the actions to the live hardware system. And so my simulation environment, all it is it's just a picture of what's happening in the real world. And then training, you can toggle on training true or false. So what this means is that if you're training, then you're learning based on random exploration. If you have it set to false, then it won't train, and it needs to use a model that's already been created. So you can pass it the model like you do down here, and it'll execute the policy that's been learned from a previous training session. These are the different AI parameters, which will be tuned depending on the AI you're using and how you're using it. Then there's the Boyd's algorithm parameters. So I'm using Boyd's algorithm to model how the pigs move. And so these are the parameters to change the behavior if you want it to be a little bit different. One of the things that I think would be really cool is after a lot of live experiments, we can collect enough data to create a better model of how pigs move. And this may even be unique to certain areas or locations. So I think that'd be really interesting to see if we can get to that sometime in the future. Game parameters, this is where you set the parameters for the game, the overarching parameters. I think the most important things here are how many subjects you want in the simulation. So here we have 5 pigs. How many defenders you want in the simulation, so 1 UAV. Currently, algorithms can only handle 1 UAV, but the framework is all set up to handle multi-agent problems and I hope that we can get there eventually. That'd be really cool. Actions, so this is where you define the actions that the agent can execute. So 0 means that it stays still, it just hovers in place. 1 goes 1 unit left, 2 goes 1 unit right, 3 1 unit forward, 4 1 unit backward. And the units are arbitrary in the simulation, but here we have some hardware parameters that map those units. So 1 simulation unit is 1 meter in real life. And so that was important for the hardware integration piece. So kind of diving into the controllers, like I said, we have a controller for a human controller. We have a rule-based controller and various AI controllers. We're also logging all the data that comes from a training session or a run. And the reason why we're doing this is so that we can evaluate performance across them. It'd be really awesome to eventually see some of these AI algorithms performing better than humans. Right now, with the sort of simple environment that we have with 1 UAV and 5 pigs, we're seeing the human performs pretty well in these situations. But eventually, when we start adding complexity with multi-agent UAVs and more pigs, I think we could see some benefit from some of these RL algorithms. The reason for adding the RL algorithm is we were hoping that we would see some emergent behavior that's not intuitive to what a human would do that would perform better and increase autonomy as well. And so I think this will all show up as we start to make more complex scenarios. I've also created an evaluation Jupyter notebook where we can come in and plot all these logs and evaluate performance of the different controllers. EMS is just the environment. So this is where the entire simulation environment is created. So this is how I created that. I just put it all in its own directory. Now, if I pull up a simulation, so this is a full simulation, and the humans in control. So the way this works is the blue dot is the UAV, the agent. The red dots are the subjects, the pigs. And then this square, this black square, is the keep out region that needs to be protected. Now, when a pig enters the keep out zone, it'll turn red and scream breach. So that's a sign that you're getting a negative reward, a really strong penalty, because that's the worst thing that we could have happen is have a subject breach our keep out zone. And then you get a small reward for being able to scare it out of the keep out zone. And so that's how our algorithm learns from feedback as to what type of policy that it wants to use, or what type of policy is most effective. Now, right now, I'm just using a human to control it, so you can have full control and you can move kind of wherever you want. Then we also have a rule-based system, where the rule-based system, it's pretty simple. What it does is it attacks the closest pig to the center of the keep out zone within a buffer. So I basically drew a buffer around this keep out zone. And if all the pigs are outside of that buffer, then the UAV comes back to home and lands to be charged back up for another mission. Now, another thing that I did is I made the rule-based system stay in between the center of the keep out zone and the threat or the subject or pig. And the reason for that is I didn't want it to accidentally get behind the pigs possibly and drive them into the keep out zone. So instead, I made the algorithm focus on staying in between the center of the keep out zone and the pigs, so that way it continues to drive them out of the keep out zone. The reinforcement learning algorithm, like I said, I had to quantize the space down, so I quantized it into a 5x5 game board, which I think is just not enough information for it to learn anything super effective or better than a human. So it still is not more effective than a human. I think more training time with the short time of the project, we weren't able to train as much as we'd wanted to after all the development to set up this architecture. And so more training time would be nice. And then I also think expanding to a deep learning approach where we can have more information as an input would be really, really beneficial for this type of problem. Yeah, and so in the future, I think it'd be really great to expand our AI and see if we can eventually get autonomy that performs better than a human, expand sort of how many agents that we're supporting with our algorithms in the environment, so we can have a more complex scenario where we can start seeing the AI outperforming the human and show real benefit. I'm really excited to see where this goes. This is all I have on the reinforcement learner, and I'll send it back to Ian.
Thanks, Adam, for that demo. If you guys enjoyed the video, please hit the thumbs up button down below. If you want to see more videos like this, make sure to subscribe to my channel. and also keep an eye towards our GitHub for updates in the future to our system. Thanks for watching, and have a nice day.